So in the last lecture we had seen the complete computational procedure, that how do we assemble the complete total structural stiffness matrix and how the matrix is partitioned into 4 different matrices. And the force vector is also consisting of 2 parts. One is the forces which are known and applied, and other are the reactions. So we club them together. So why we have included these? Reason is that we want to have reactions directly. Otherwise there is another procedure by which you can get the reactions, but here we have chosen this so that we get reactions in a single go. Now the next question is, which of the 3 matrices they are important? We need only 3 matrices. We don't need 4 because symmetry is there. So we need KPP, one of these 2, and KXX. That's all. And then which among these is the most important matrix? Or which will be the largest matrix? KPP will be the largest matrix. And KPP will be part of all our computations. So whether we solve the equations, we have this support settlements, either they are 0 or they are known value. So if they are 0, then our equation is simple. Just P equal to KPP into UP. We solve it. Otherwise, we have to find a modified force vector P. So whichever case, this KPP matrix is very important. So problem is that KPP in general, it will have very large size. So we just see some simple strategies how we can reduce our memory. So because it's a very large matrix, but then we take advantage that it's symmetric, number 1, and number 2, it's banded. It will have lot of 0 elements. So something like this. The matrix will be something like this, that after a certain band, which may be regular or irregular, we'll find that all the elements they are zeros. So the common approach is that we don't store the entire matrix. First of all, we need only the upper or the lower, taking advantage of symmetry. And number 2, it's banded also. So what we do is that we store this particular band in a rotated form like this. We don't need to store the entire matrix. Just one triangular half, and that too up till a certain band. And we rotate it. And we artificially create some of these elements which are zeros. So that's how we will store our matrix. Because this makes a huge difference. You may find that if our KPP is 300 by 300, you may find that the band size is only 30, 40 or 50. But now question is, why it is banded? Symmetry we all know, because of the Maxwell-Batty's theorem, a matrix is symmetric. Kij, K equal to Kgi. But why it is banded? What is the reason that a matrix is banded? Let's say we have a structure. Let's say this could be a plane frame with a large number of base, and it's continuing. And let's say we have done the numbering of the joints like this. Now here we'll use the matrix stiffness approach just to understand this. Means we'll use physical interpretation just to understand this. Then we'll see the computational procedure also. How does program find the bandwidth? But for understanding, let's say we want to find a particular row or column of the matrix. So what should we do? If by first principles, by the matrix stiffness approach, means manual method, we want to find a particular column. What is the procedure? We apply unit deflection along that particular degree of freedom and find out what are the forces generated along various other degrees of freedom. They will be the particular column. So let's do this process that we have here degrees of freedom 4, 5, 6 at joint number 2. So let's say we apply a unit rotation here and log all other degrees of freedom. So we have applied this, what we have enforced, and now the forces generated along various degrees of freedom, they will be the 6th column of the stiffness matrix. Now you see the values. So we have applied here this unit rotation, and which forces or which kind of members they are generated. Let's say this is the 6th column. So now what will be K66? K66 has a positive value, so we mark here a tick. Now what will be other terms? K7, will it be there? K76, where is the 7th degree of freedom? It will have some value?
0.
Then 8, number 8, will there be some value for number 8? 8 may have some value because it is connected by the member. The member is undergoing deformation, so it will have some value. But we can go on, and we'll find that what will happen after this. If we go to the next joint, what are the degrees of freedom? 10, 11, 12. Will they be involved? They will not be involved. Why they are not involved? Because we have just established precedent here. Nothing flows beyond this. But after this, nothing. So this is the limit. Beyond this, all values they are 0. So that's the basics of why it is banded in nature. Because the bandwidth is dictated by what? The other degrees of freedom, they are connected through members only. So it will depend on what is the highest other degree of freedom which is connected. So all depends on how we have done the joint numbering. So beyond this, everything will be totally 0. And this is a fact. Degrees of freedom which are related by member, they are connected. And if they are far away from one member length, they are unconnected. They will not have Kij, corresponding Kij. So that's the reason for the bandwidth. So what we do, now we make this as a rotated banded matrix. This was Kii, let's say. This goes here and it becomes Ki1. Right? When we are rotating, rho is the same. Rho does not change. But the column number changes. What is the new column number? Because II becomes I1. So there is a reduction of I minus 1. So that's why we say that if the original column was J, final column in the rotated matrix will be J minus I plus 1. Correct? That's how, if J is equal to I, we land up in the first column. And J equal to I plus 1, we land in the second column. So this is the thumb rule. This is how we get the column numbers. And Kii goes to Ki1. And we can do in the other way also. Let's say we know a particular element of the banded matrix. So where it will go, like here we have C equal to J minus I plus 1. So where will it go in the main matrix? Its original position is J, which is C plus I minus 1. So both ways, if we know a particular location here, we know what location it will go here. Or in other words, if we know a location here, we can find where was its original location here. So for all practical purposes, we will not store our matrix in this, we will store the matrix here to optimize the space. And all the operations we will do on this, all computational operations. So we have to make sure in the program, if we want to do some operation on Ij, then the corresponding element will be I, J minus I plus 1. So we have to replace J by that substitution so that we can seamlessly do all the operations. Alright, so why we are doing this? To save our space. and of course time also, because program when it goes through, it just sweeps through the zeros, so it's wasting its time. So I is the your row and C is the column in the banded matrix. So this left hand side is in the banded matrix and the right side is in the original matrix. So now can you tell me how does program compute the bandwidth? We have just seen how physically we can compute the bandwidth by physically seeing what is the connection ij, what ij will be related. But how does a program calculate the bandwidth? Program cannot do the way we have done in the matrix stiffness approach. Physically program cannot do. So what should program do and how it should do?
So it is applicable to the rigid frames.
Mm-hmm.
This formula and
We are deriving it for 2D frames, but it's extendable.
rigid joint.
It is extendable. Very easily you can extend it when we go to the next phase. Right now for derivation of the basic things, we are assuming everything simple. So my point is, how do we compute R? So I give you a formula. Formula is that, what is the basis? Basis is members, they connect the degrees of freedom. Only those degrees of freedom which have a member in between, they will have some relationships in terms of Kij values. All others will be 0, right? So program has to execute these steps. First of all, for each member, it has to find, because it has the member degrees of freedom, it has the structure degree of freedom. For each member, it has to find what is the maximum degree of freedom, what is the minimum degree of freedom, plus 1. Let's say we have a member like this. This is some member number M, and on this side we have joint number 3, and this is not the consecutive joint because we are, let's say, numbering horizontally. So after going through all different numbers, then when it comes in the next row, so this number could be different. Maybe this number could be 30. So for this member, what is the lowest degree of freedom? Here we have 3 degrees of freedom, 7, 8, 9. And here we have the degrees of freedom. The last will be 90, 89 and 88. So what will be the x term for this member? 90 minus 8 plus 1, right? So x will be 84, right? So the member which has the largest gap between the two end joints, that will dictate the bandwidth. So finally, when it does over all the members, then the highest of the values will be equal to R. So this loop has to be done covering all the members. Alright, so that's the bandwidth. Why we have plus 1? Because we have the first column. Ith diagonal element goes to the first column. There also there was plus 1, so here also there is plus 1. So you have understood what is the basis of this algorithm. So let's take this example, and how would you like to number this? Horizontally or vertically? Horizontally or vertically? See, we can number it like this, or we can number like this. Will that make any difference? No. Okay, so let's do the numbering and then come to conclusion. We have done all the joint numbering, and similarly you can do member numbering also if you want. Now we have to find this x value for this particular structure. What will be the value of x? We have sequential numbering. You choose any beam, it will be same for all beams because we don't have any break. They are just related by just one plus, that's all. So what will be the bandwidth for this member? X, I mean the value of x. The largest degree of freedom minus the minimum degree of freedom. 6. And you can find that for all beams it will be 6 only. Next column. Column has a larger difference. So, but columns also, they are also sequential. So it does not make difference. So we don't have to do it for this column because this goes in the x side. It does not contribute to kpp. This will contribute to kpx. So we can leave these members. So all these members what way will these contribute to the value of x? Let's say a typical column. Let's say we do for this column. What is the lowest degree of freedom? 7 and 9. So minus 7. And what is the highest degree of freedom? 24 plus 1. So what is the answer?
18.
So answer is 18. So here for this particular structure, the largest value of x will come out to be 18. So bandwidth is 18. So the size of KPP, what will be the total size? 60. 60 is the total size. So if we now make the matrix here for the complete structure, the overall matrix size is 60 by 60. And what is the size of KPP and KXX? X, how many? 1, 2, 3, 4, 5, 15. So this is 15 by 15 and 45 by 15 by 15, and this band will be 45 by 18. So you see here that bandwidth is small, and imagine if the frame was very large, it would make a lot of difference. Now let's erase this and do the other numbering. So just remember what bandwidth we had got, 18. Now I am erasing everything and I do vertical numbering. So when I do vertical numbering, I have to follow the rule that I will come to the restraint joints in the end. Okay, now we repeat the same exercise. Now what will go on the bandwidth, column or beam? We need not find for the columns, taking Q from our last calculation, because all the columns they will have lower x value. Beams have larger gap. So beams, and choose any beam and it will give you the value of x. Value of x will be same for all beams. So what value we get for x here? Highest is 12 minus 1 plus 1. So answer is 12. So the bandwidth in this case will be 12. Earlier case, what was the bandwidth?
6.
Not 6, 18.
18 maximum.
Earlier case it was 18 and here it's 12. So has it made difference or not? It has made difference. We may not appreciate here, but in large structures this difference could be very outstanding difference, because not just the memory, sometimes when we run, if our structure is too big, we get the message that we cannot have more, the number of joints is more than permitted. So basically is this problem that the size is so large that the program says that it's beyond its reach. So numbering has to be done such that we get lower bandwidth. So how we should number? If we have a continuous building, just a 2D frame, what should be the guidelines for numbering? Because we now know basically it's the repetition when we are going like this. So here, like you have seen, that it's ideal to number them vertically. Right. So the thumb rule is that if you have a very long building, like our blocks, very long building, but the number of stories less, number of ways more, then how we should number? So it's ideal to number it vertically along the lower dimension. Lower dimension means in terms of the nodes, not the dimension in terms of the value of the length, but in terms of the number of nodes. We are getting less number of nodes here, so when you go to the next level, you will have less difference. And on the other hand, if you have a very tall building, tall in the sense that it has large number of joints in the vertical direction and small in the horizontal direction, then how we should number? Horizontal. We should number horizontally, because then we get less difference between the two end numbers of a particular member. So that is the main reason how we should number. So like here we have seen, if we do horizontal numbering, bandwidth is 18, do vertical numbering, bandwidth is 12. So our numbering does make difference. Internally, in the way the parameters are saved and used, it does make difference. Now one aspect of computation is still there, and that aspect is that we have to find one inverse. In the whole operations, one inverse is to be found. And what is that inverse? KPP inverse. Because if your support settlements are 0, your UP is simply KPP inverse into P. And if, for example, your support settlements are not 0, then it will be simply some P dash, which is the modified force vector. So in any case you have to find inverse. Now how do we find inverse? Do you know any algorithm to find inverse? We don't have to do manually. Like the way we do, we find the adjoint and we find the determinant. No, it has to be done computationally. So you know any algorithm which does it? We'll just introduce you one particular approach, that is Cholesky's algorithm to determine the inverse. See, before MATLAB was there, we used to write code to obtain the inverse of matrices either in Fortran or C. So thing is that we have to find inverse of this. If support settlement is 0, we have simple equation. If support settlement is not 0, then we have P is replaced by modified P. So now here we have an advantage. What is the advantage? Our stiffness matrix is symmetric. So we take advantage of that. So that means we can always write it as a product of two triangular matrices. K is symmetric, but it's not triangular. Kij is equal to Kgi, but does not mean it's triangular. But we can always write a symmetric matrix in terms of a product of two triangular matrices. They are simply the transpose of each other. So if K were symmetric, then we can always break it down. It can be mathematically proved. We are not going into the proof. We are not going into the proof of the Cholesky's algorithm also. We'll just using it as a tool. Now once we have done this, then we can very easily find the inverse without actually doing the operations of the inverse. So we'll find solution without actually doing the inverse. So we call this as V matrix. So V is sort of an upper triangular matrix. So a product of these two, that gives the symmetric matrix. Only condition is that this has to be symmetric. When you say we find inverse, essentially what it means, if I solve this system of equations, that means I have done my work. So here we are writing K as a product of two these triangular matrices together. And let's do one manipulation. Let's write it like this. So V into U, V is a matrix, U is a vector. One matrix is n by n, other is n by 1. So their product will be what? N by 1. It will be a column, right? So we have here V transpose multiplied by W equal to P. Now can you solve it? Can you solve it without finding inverse? If I ask you find all values of W, you can find it because it's triangular in nature. It's like this. Here is V transpose and this is your W matrix. How do you find? You find one by one. First solve this, because here incidentally all other terms are 0, so they get cancelled out, you know, V1. Now go to the next equation. Next equation you already have one variable known. Next you can find W2. Now W1, W2 is known, you can go to next equation. So like this you can go on and on. And at the end you will have W matrix. And then our goal is to find U matrix, so just make use of now W. W we have found now. So now solve this equation. Only difference is now in terms of V transpose we have V. So it will be the other form of the triangle. Like this is lower triangle, that will be upper triangle. Now we solve the upper triangle. Can you solve it now? You can solve it. Again, row by row, beginning from the bottom. Like this we started solving from the top. This we will start from the bottom. So in the end what we get? We get U without actually finding the inverse. We have not done the real process of inverse. So even if the matrix is very, very large, so just by these simple operations we are able to find it. But then the $1 million question, how do we convert this K into V transpose V? How do we do that? That we have not answered. So that is provided by Cholesky. Cholesky, he was a Russian mathematician. So he basically formulated this technique called as Cholesky's algorithm. So this is the crux of Cholesky's final equations. So he begins with the first term is basically k11 under root. Because k is known to us, we have assembled it, kpp, essentially it's kpp. The first term is k11 under root. And the first row, this gives for the first row. For first row, we have to divide by the first row of the original matrix divided by k11, v11 which we have found. And then all the diagonal terms. And then all the remaining terms, they are given by this equation. So like this, these all steps we get the complete matrix. And we ij0, when I is greater than j, that means, what does it mean? I is greater than j, basically it's giving us the upper triangular matrix. So lower triangular matrix, all the terms in lower triangle, they are 0. So this simple algorithm, if we use, then we can very easily get the displacements without actually finding the inverse. In fact, to get the inverse also we can use this algorithm. We can find inverse also just by using this algorithm you write the system of equations. See, matrix multiplied by x inverse will give 1. So by that logic we can use this to find the inverse also. Okay, so this is the entire computational procedure. So in fact we can take further advantage that both V and V transpose, we need not create. See, when we write a program, we invoke variables, temporary variables in the volatile memory. So here V and V transpose, we need not duplicate our effort. Just one of them is enough. If we need any term of V transpose, just we take the corresponding term from the lower or the upper side of the other matrix. So both of them will also be banded matrix. If your original matrix is banded, these will also be banded. And bandwidth will also be same. So these also we can create in the banded form. And we generally, to save the number of variables, if we are dealing with V, then we can just overwrite on KPP itself. Because many times in order to save the number of variables, we overwrite. We need not create so many space in the random access memory. Otherwise our computer may slow down. So these are the various steps of the complete process. Any doubt, any question till now? This is the central part of the formulations, the direct stiffness approach.